Hello, my name is Kees van den Doel. I'm at Adrock. We are a company based in Edinburgh, Scotland, and we're specializing in subsurface exploration using low-frequency radar waves. This talks about monitoring subsurface temperature using radar scans with machine learning and applications to enhance oil recovery using thermal injection. Collaborators on this work were Colin Stove, Michael Robinson, and Gordon Stove. I'll start with a brief overview of enhanced oil recovery methods. These methods allow up to 60% oil to be extracted from reservoirs, and this is done by making oil flow easier by reducing their viscosity, increase the mobility ratio. Popular methods used in the industry currently are gas injection and thermal methods. We are focusing on thermal methods. Steam injection is a very popular thermal method. You inject steam in the ground to make the oil hot so it flows more easily. For this to work without problems, you need to monitor the subsurface temperature profile, make sure steam goes the right direction and nothing goes wrong. And currently, the only reliable methods to do that is using temperature observation wells, TOWs. These are expensive. First of all, you have to drill a hole. Then once you have the well drilled, a typical cost of a measurement, basically lowering a temperature in a probe down the hole, is about $5,000 per well for a single measurement, and the well has to shut down during the measurement. All these costs result that the measurements are typically done only 3 to 4 times a year. It would be very nice if you could do it more frequently, because if something goes wrong in the meantime, it can be very expensive. So what are the properties we would like an ideal temperature monitoring technology to have? The wish list is we want to do it without drilling. We want to measure subsurface temperature using only surface data. We want to measure without well downtime. We want to have fast acquisition, frequent monitoring, low cost per measurement, and easy data processing. So we made an attempt at this using our technology. So temperature monitoring with electromagnetic waves sounds impossible, because what does temperature have to do with electromagnetic wave? Well, a temperature affects the subsurface electromagnetic properties such as conductivity and dielectric permittivity. So those affect responses from waves propagating in the ground. We make use of this fact by using our pulsed subsurface imaging system, which sends low frequency waves down the ground and detects their reflections. The low frequency means that the wavelength of the waves is of the same order of magnitude as the actual objects, the high temperature clouds, if you like, we like to detect. So a direct imaging of the returns is not going to help us. So we typically do bistatic data acquisition, and we stack about 100,000 shots for each measurement. Takes about a few minutes. And we experimented on a producing oil field where we had access to 20 well TOWs, actual subsurface temperature data. And we used this as training data to map our radar data to temperature data for these training wells. And then we tried to see how well this worked on blind tests. So the methods is summarized here. Both temperature well data and our data are time series, and we use some machine learning, basically neural networks, to map the temperature to the electromagnetic data. And then there's some details here, and then we try how it works without temperature wells. So here are the results of 21 blind test results. The green ones are another oil field, which I'll say a few things in the remaining seconds. And the results, which you can study more in detail reading the paper, are encouraging, though perhaps not ready for prime time yet. So the red is the actual data we want to get, and the blue is our reconstruction, blind reconstruction using our data. And I'm running out of time, so I will not mention what the green ones are. These are data from a different oil field. So it shows basically that the training is site-specific. Brief conclusions, we find the results are encouraging. Local variations in the ground conditions can spoil the result. And there are several methods that we can, several paths to travel in order to improve these results. We can incorporate ground condition data geological data. We can use more sophisticated neural networks, use autoencoders. And finally, why does it work? Well, electromagnetic waves penetrate apparently sufficiently deep. And it could be that what we're seeing is similar to the apparent seabed imaging you can get using conventional radar from airplanes, because there is an interaction between the surface and the subsurface, which sort of projects an image to the water surface. Here we get an image, if you like, of the temperature projected on the surface, which we measure. Thank you for your attention.